Hello. Let's talk about solving equilibrium problems when we know the starting concentrations of reactants or products, and we can use that to determine the concentrations or the relative amounts of each once the equilibrium in a reaction is reached. So here we have the dimerization of NO2 to form nitrogen tetroxide. And so NO2, nitrogen dioxide, is a brown gas, and over time it forms an equilibrium with N2O4. So if we have a scenario where we start off with pure NO2, over time the amount of NO2 will decrease and the amount of N2O4 will increase. And so if we look at this in terms of, say, partial pressure, if we start off with no N2O4 in the container and some amount of NO2, we can then measure the concentrations of equilibrium. And for this reaction right here, the pressure-based equilibrium constant is 6.84. So let's remember that the equilibrium constant is expressed as products over reactants. So it is just the partial pressure of N2O4 over the partial pressure of NO2. So if we start off, say, with the partial pressure of NO2 as 1 bar and 0 bars, so no NO2 in the container, we can then figure out how the reaction, as the reaction progresses, we can calculate what the relative amounts at equilibrium are based on the equilibrium constant, because we know that the ratio of the partial pressure of N2O4 over the partial pressure of NO2 squared has to equal 6.84. And to do that, we use an ice table, and for that we just write out the balanced chemical equation, and we first write out the initial amounts of each reactant and product. So also, if there's product formed, we also need to write that down as well. So in this case, we start off with 1 bar of NO2. And so let's leave the units out in this example right here. So the initial, I for initials, is 1 bar. Let's leave the units out. And we have no N2O4 in the container, so we can write this as 0. Now we're looking at the change, so we know the amount of NO2, the partial pressure of NO2 in the container is going to change, so it's going to have a negative sign, so it's going to decrease, and it's going to decrease by an amount of 2x because of the coefficient of 2 in front of the NO2. And likewise, the amount of N2O4 is going to increase, so this will have a positive sign, and it will be just x because there is no coefficient, or the coefficient is only 1 here, and that is also seen in our reaction profile right here, where we see, based on the stoichiometry, NO2 decreases at twice the rate at which N2O4 is being formed. And so that those reaction coefficients play a role in how much product is being formed, of course. That's the whole principle behind a balanced chemical equation, is to figure out how much product is being formed. So, and then for the E for equilibrium conditions is then going to be 1 minus 2x. We just add everything up from above. 0 plus x is x. And that is now our equilibrium condition that we can write out into our equilibrium. And now we can express like we did in the preceding page, and write out, instead of writing these partial pressures, write out this equation with these variables right here. So we've got the partial pressure of N2O4 as x over 1 minus 2x, and now all this has to be squared. And now this has to equal 6.84. which equals k. Now what we need to do is rearrange this equation, so now we can solve for x. And let's do this. We can expand this factor in the denominator here, and so we end up with 1 squared minus 4x plus 4x squared, and that equals 6.84. Now we can bring all this in the denominator and multiply it by 6.84, and then bring x over to make it to make the whole equation equal to 0, which is the form of a quadratic. So once we do that, we end up with 6.84 times 1 is 6.84, and 6.84 multiplied times minus 4 makes minus 27.36x, and 4x squared times 6.84 makes plus 27.36x squared. Now we want to bring this x over to the other side, so we subtract x. So we can now rearrange this equation. So we obtain now, with the x brought over to the other side, we have now 27.36x squared minus 28, so because we subtracted x, so we start with 27, and plus 6.84. Again, we want to rearrange this equation to the format of ax squared plus bx plus c equals 0. That's what we want to rearrange this equation to, so we have this right here, and now we can solve this as a quadratic. You can use the quadratic equation then to solve for x, or you can program this into your calculator so you don't have to remember and enter this every single time. I recommend you do that, or use one of the online quadratic equation solvers that are available, such as this one. And here's one that is convenient to find, so just Google quadratic equation solver, and usually this one comes out first at this site called Math is Fun. And so there, all you have to do is enter the parameters here. So we've got 27.36x squared and then make sure you watch the signs, minus 27.36, 28.36, and for C we have 6.84, and we end up with these two roots right here. So 0.655 and a bunch of more numbers right here, or 0.382. And a bunch more numbers, that's probably enough. We only need 3 or 4 decimals here. So let's take a note of those. And here let's evaluate these two roots right here. We can see that 0.655 is not a plausible root because it would mean that we have too much material. So if we insert this back into this equation right here, 1 minus 2x, and we use x as 0.655, we end up with a negative number. So we cannot have negative matter. We cannot have the concentrations go negative. So that number would not be plausible. Only that second number would be plausible. So we can state that this first solution right here is not plausible, and the second one is the plausible one. So this now represents the partial pressure of NO2, N2O4 in bars. So now we know all the solutions right here, and then we also know from the ice table right here, we can also then figure out the partial pressure of NO2, and we can then plug that in. So we then have the partial pressure of NO2 is 1 minus 2x. Plug that x in that we just calculated, so 1 minus 2 times 3.82, and we end up with 0.236 bars of NO2. So now we know the final concentrations for all these. So now we know the final concentration, or the final partial pressure of NO2 is 0.236 bars. And the final concentration of N2O4 is 0.382 bar. Thank you for watching. Here a quick challenge question. I look forward to seeing you in the next class.